What I'll do is I'll try and do a few of those questions. Starting with the first one, let's try and do this one. He's saying the first question, most of them are going to be very straightforward. It's just 3-4 things that they're going to ask you about. So the first one is, why is the entropy change of the reaction one is positive? Why is it positive? Because there's a gain of disorder. Why is there a gain of disorder? Because the moles of gas, they increase, or a gas is being produced. So that gas is going to create a lot of disorder. Initially you had solids, now we've got a gas. Then he says that reaction one is highly endothermic, suggests the effect of an increase in temperature on the feasibility of the reaction. So the feasibility depends on the Gibbs free energy, that's the total energy available to the system. So the formula for Gibbs free energy is, that formula is delta H minus T delta S. Now they've told us already, what have they told us? That it's a highly endothermic reaction. So the first term is positive, right? So delta H is positive, that's the first term. And the second term is delta S, which is also positive. It's very positive. So that's also positive. So if that is positive, because of the negative sign over here, this entire thing would actually become negative, right? So delta G is going to be it's going to be negative. When will it be negative? When the negative term is bigger in size. When is the negative term bigger in size? When T is large, right? Because if you have a larger T, this thing would have a bigger value, and because it's got a negative sign, it's going to have a negative value. So that means Gibbs free energy would be exothermic when T is large. So this is what you're going to write. You're going to state that the term D delta S becomes more negative when T is large. Hence, delta G becomes negative. That's it. I'm going to write down the statement as well. I mean, the statement must have been written over here. I think the marking schemes were with this. So as T increases, D delta S becomes bigger, or it becomes bigger, or you can say minus T delta S becomes more negative. So delta G would become more negative because of that. Is this part clear? This one? You clear? Yes or no?
Yes.
So then I'll calculate delta S. So what is delta S? Delta S is the entropy of the products, and you subtract the entropy of the reactant. So it's the difference between the products and reactant entropy. So the products are over here. I think he's asking for the entropy change of reaction number 2, this one. So my product is, one of them is 314, and the other one is H2, that's given as 131. And my reactants are, so what are my reactants? My reactants are silicon. One second. So one of them is silicon, that's 19. And the other one is HCl, and 3 of them. So that's 187 times 3. So you just find the value, which probably is already calculated somewhere. And that's minus 135. I'll keep your calculator with you. I'm not going to look at the marking scheme now. But is this clear as well? This question, right? Clear? Is this clear? Yes or no?
Yes, sir.
So you've got the other question. Reaction 3 is the reverse reaction 2 and used to obtain pure silicon. So this is reaction 3. Use this information in answer to P1 to calculate the temperature in kelvins at which the reaction becomes feasible. So again, delta G should be negative for the reaction to be feasible. So that means delta H minus T delta S must be negative, which means it should be less than 0. You got to solve this inequality. So delta H is already given, that's 219, and remember it's in kilojoules, so that's 219.3. Temperature is what we have to figure out. Delta S we've calculated in B1, which is over here, which is minus 135. So we've calculated delta S minus 135. So this thing actually becomes positive, and this is less than 0. So that means, what does that mean? It means that T 135 is less than minus 219.3. Get there's one mistake that I've made. Does anyone recognize that mistake? There's one mistake that's been made over here.
The sign changes.
No, not the sign changes. It's that enthalpy changes in kilojoules, and remember entropy changes in joules. So this 135 should be when you're using this, they should all have the same unit. So delta S must be in kilojoules as well. That's going to be, you're going to divide that by 1000. Is that clear? You can remember this is one thing that I told you that that entropy change and enthalpy change, they have different units. This is kilojoules, this is joules. So make sure you make the unit the same when you're doing this calculation. So what do you get for this? Has anyone done this? Although it's given away, it's 16. 24.4 Kelvins. Make sure you, I mean, if somebody can check this, are we getting the same thing? Can you anyone? Lisha, do you have a calculator?
624.
I mean, this thing, right? What is meant by the entropy of a system? That's the measure of a disorder of a system. That's it. NaCl dissolving in water. So NaCl dissolving, that's more disorder being created. So that's positive, right? Why disorder? Because when you're dissolving it, the crystal is breaking up into pieces and the ions are dissociating. Water is solidifying to ice. That is less disorder. That's delta S negative. That's a decrease in disorder. So that is delta S negative. Less disorder being created. Over here, he's saying that the evaporation of 1 mole of water has a standard Gibbs free energy of delta G of plus 8.6 at 25 centigrade. Sketch the graph on the axis to show how the delta G changes for this process between 25 and 150. So at 101 kilopascal. So what's the relationship between delta G is equal to delta H minus T delta S? So first thing is we just need to figure out. And remember, he's talking about water. So the starting point is somewhere positive. That's 8.6. That's your starting point, right? So at 25 centigrade, that's 8.6. Sketch a graph to show how the delta G changes. So delta H, for what process? He's saying the evaporation of 1 mole of water, right? So evaporation of water, right? So it's H2O liquid changing into H2O gas. What do you think? Because remember, he's talking about evaporation. So delta H, I think that's endothermic, right? Is that clear? That's endothermic, right?
Yes. Yes.
And delta S, entropy change, that is also more disorder, right? It's turning into gas, right? So both of them are positive, right? So this is positive and this one is also positive. But because of the negative sign, this thing would actually become negative. I said, now comment on this. Who's going to tell me that what will happen if I increase temperature? What will happen to the value of delta G? Would it become more negative or more positive? What will happen to it?
More negative?
It's going to become more negative because T increases. Then the negative part would become bigger in size. Hence, delta G would become more negative. So I guess, and when do you think evaporation of water becomes feasible? At what temperature does it become feasible?
At high temperature.
At high temperature, but exactly at what temperature does it become feasible?
100 degrees centigrade.
So that means delta G would be less than 0 above 100, right? So the graph would actually go like this. It's going to be, before 100, it's going to be non-feasible. It's going to have a positive value, right? And as T increases, it's going to become more and more negative. So at this temperature, it becomes becomes negative. Is this graph clear? Do you understand this graph?
Yes.
I mean, from the values, we were able to figure out that it becomes negative, but the exact point is 100. At 100, beyond that, it becomes very feasible. It becomes more and more negative. Okay, the reaction. Is this clear? Is this clear? Anna, is this clear? Anya, Shan, is this clear? Over. So next one, we've got. Let's try to do the other one. That's I've got the reaction between A and B is feasible at low temperature, but is not feasible at higher temperatures, right? So, okay, so, and he's saying predict what the sign is, right? So it is feasible at low temperatures, but is not feasible at higher temperatures. So I know. So now we have to like make some guesswork. So as I've got minus T delta S, just a second. So I've got this one. Then I've got delta H and minus T delta S. So he's saying it's feasible at low temperatures, right? So at low temperatures, when the temperature is low, it is feasible. That means delta G must have a negative value. And at high temperatures, delta G has a higher value. It's not feasible, right? So at low temperatures, delta G is less than 0. At higher temperatures, delta G is greater than 0. So you've got two things. Delta G, I mean, this is what the scenario is. Is that clear, this thing? Alicia, is this clear? Vacuum clear, is this clear?
Not really. So could you explain this?
They're saying that at low temperatures, it is feasible. So what is the value of delta G at low temperatures? That's less than 0. That's negative, right? You clear it?
Oh, yes.
And at high temperatures, saying it's not feasible. At high temperatures, delta G must be greater than 0, right? Just a second. So at high temperatures, delta G must be greater than 0 because it's going to be positive. It's not feasible. And I'm just going to write this down. Because this means feasible. This means not really feasible. So I need to figure out what delta H and delta S are. So remember, low temperature, it is feasible. Low temperature, let's say temperature is 0. If temperature is 0, this term becomes 0, right? Low temperatures, right? Negligible. I mean, this thing disappears. Is that clear that at low temperatures, I'm taking the temperature to be 0, right? So at low temperatures, the reaction is, so at low temperatures, the reaction is feasible. So what is the value of delta H? Is it negative or is it positive? What's going to happen at low temperatures? Again, let me restate this very clearly that at low temperatures, he's saying that the reaction is feasible. At low temperatures, this term over here disappears. Let's say the temperature is so low, it's 0 kelvins. This term disappears. And he's saying that the reaction is feasible at low temperatures. That means delta G must be negative. The only way it could be negative is that delta H is negative. Do you understand this part?
Yes.
Does everyone understand? Shan, do you understand this, Ania, Fatma, Anna? So one thing I figured out that delta H is negative, right? Because at low temperatures, the only way delta G could be negative is that this is negative. And then he says that at high temperatures, it becomes not feasible. That means delta G becomes positive, right? Now, the only way it becomes positive is that when I go to a bigger temperature, so now talking about higher temperatures, right? So if I take a higher temperature, so if I take a higher temperature, this value becomes bigger. But he's saying that it becomes not feasible. That means this thing becomes positive. Now, the only way that is possible is that this entire thing has a positive value. That's the only way that this thing becomes positive at higher temperatures. And so at higher temperatures, this thing will have a bigger value. But the reaction is becoming not feasible. That means this thing is turning into positive. So that this entire thing is positive. Now, the only way this entire thing is positive is that delta S must be negative, because two negative signs would add up to make it a positive value. So that means delta H is negative and delta S would also be negative. Both of them would be negative for this entire thing to work. So I'm just going to repeat this. Some of you might be getting confused with this. So I'm just going to repeat everything that they stated. At low temperatures, the reaction is feasible. So at low temperatures, this thing disappears. It becomes very small. Smaller T, let's say T0, this thing disappears. He said the reaction is feasible. Now, the only way the reaction is going to be feasible is that it's going to be negative. And the only way this is going to be negative is that delta H must be negative, right? And so both of them would be negative. So that is where we got that delta H must be negative. And then he says that at higher temperatures, it becomes not feasible. So that means it becomes positive. So at higher temperatures, this thing becomes bigger in size. And if this becomes bigger in size, it must have a positive value. That's why delta G becomes positive, right? So how can it have a positive value? It can only have a positive value is because delta S must be negative, because the two negative signs would add up to give you a positive value. So only that way this thing gets a positive value. And at higher temperature, you'll have a bigger positive value and delta G would become positive. So in a way, both things would actually turn out to be they'll turn out to be negative. Is that clear? And is this clear? Yes or no? We actually did a graph on this. I'll just go through the graph as well. Not a graph, but a table. Just a second. So we went through this table where we predicted all the reactions so this one, negative at lower temperatures. When would delta G be negative at lower temperatures? When both of them are going to be negative. We did discuss each one by one, where I told you what if a reaction, both of the values were negative. This term would then become it would become actually positive because of the negative delta S. The two negative signs would add up and this would become positive. So one of the terms would be positive, the other one would be negative. The only way this would be feasible is going to be at lower temperatures, because at lower temperatures, this thing will disappear and delta G would have a negative value. Is this question clear? This one? You clear? Yes or no?
Yes.
Is this? So just make sure we did go through the entire table, and the explanation for this is given over here. I mean, both of them are negative. So as temperature increases, delta G becomes more positive. So at lower temperature, delta H is more negative, or delta H is more negative than delta S, T delta S. And at higher temperatures, the T delta S becomes more positive because it becomes bigger in size. As anyways, a few more questions. We've got I think he's asking you to calculate delta S over here. So you're going to calculate this same way, which is products minus reactant. So these are my products, lots of them. So products minus reactants. And the products are going to be into, that's 192 into half. So can somebody do the math quickly? O2 is 205 into half. And then I2 is gas, that's 261 into half. And minus NH4IO3, which is 42. Kya hai iska answer? What are you getting?
$287.
So you're getting 287, right? And remember joules per mole per, I mean, whatever the units over here are, mole per Kelvin or joules per Kelvin per mole, same thing. Over here, you're getting 427. What's 2 into 70? As I missed out H2O. I forgot to write H2O. I missed out on H2O. Let me correct this error. That's in my products, I had 2 H2Os as well. So that's 2 into 70. So I'm going to get 427 for this. So products minus reactants. And now again, the reaction is feasible at all temperatures. Explain by using the data in your answer to F1. So feasible at all temperatures. Again, we did this in class as well. Some reactions are going to be feasible at all temperatures. So always negative. So you have delta H negative and delta S positive. That combination would make it a feasible reaction always. And why would it be feasible? They gave you the enthalpy change. So I'm going to explain this again. It's delta H minus T delta S. I mean, this is the only part that is confusing, where you have to predict the feasibility of the reaction. So remember, you have to make it delta G negative for it to be feasible. So enthalpy change is negative, right? And entropy change, you just calculated, it gave you a positive value. So that means this side is positive, but it's got a negative sign. So that makes it a negative value, right? So both values are coming out to be negative. So the answer is that no matter what the temperature is, this term is also negative and this term is also negative. So delta G would always come out to be negative. And you're going to explain this over here. So delta, I mean, the explanation is delta G is always negative. Why? Because minus T delta S is always less than 0 for all temperatures, and delta H is also less than 0. So both of the terms are negative. So the entire expression becomes negative. Let's clear the last one.
Yes.
So now this one, we'll calculate delta S quickly. So again, products minus reactants. So delta S is products, that's Ag plus 172.7 plus Cl minus 1, that's 56.5. Minus the reactant, which is AgCl solid, that's 96.2. What do we get for this?
33.
You're getting 33. Point what? As I remember, follow the convention that if it's 3 significant figures, your answer should be 3 significant figures. So it's 33.0. Make sure you write that 0. That shows accuracy, that you know that the first decimal is 0. If you just write 33, that just means that you're not sure what this is. It could be 33.1 or 33.2. If you write 0, that means you're sure that it's 0. So now explain with the aid of Hanji.
I'm getting 33.3.
This is 56.5. So maybe you took it as 8.
Oh, yes.
As anyway, so with the aid of a calculation, why delta AgCl is insoluble in water. So that is feasibility, right? Because we need to figure out dissolving, is it feasible or not feasible, right? So all I have to do is calculate delta G. Delta H is already given, that's 65. So I just have to plug in the values. Just be careful about the units. This is kilojoules, and this one over here is joules. So make sure you get the units right. Either all of them should be kilojoules or all of them should be joules. So it's 65.5 minus T. What temperature is he talking about? The temperature must be in Kelvins. It should be 298 into, so this is 298, and multiply that by what?
Sir?
Haji.
Every time we take it in Kelvin.
Temperature is always Kelvins.
Okay, sir.
And make sure when you're using this equation, make sure either take all of them as kilojoules or all of them as joules. Both ways it's going to be the right answer, but one of them in kilojoules, the other one is joules. That's going to give you wrong answer. As anyway, so delta T delta S. What is delta S? Delta S is 33.0, but that needs to be divided by that needs to be divided by 1000, right? So what do we get here?
$55.7.
55 point. And
Seven.
so the important thing is you're getting a positive value. So that means it's not feasible, right? So the question was why, with the aid of a calculation, why it's insoluble? Why is it not dissolving? Because it's not feasible. That's the answer. TK. So delta G is positive, so it's not spontaneous. It's not feasible. I say entropy. That's a measurement of a measure of a disorder of a system. Liquid water at 80 is cooled to 60. So the entropy change is what? Negative or positive? Less disorder or more disorder?
Less disorder.
Okay, so delta S is negative. And why? Because the molecules are losing kinetic energy, and so there'll be less disorder, or although there won't be much difference because at water at 80 and water at 60, they kind of look the same. I'll check the explanation for this just to confirm the reasoning for this one. This one is probably one of the latest papers. So it is negative, molecules have less energy. So that, I mean, he's making the same comment as well. So less kinetic energy. So that's it. But very little difference. Water at 80 and water at 60, the change in disorder is very, very slight. Calcium chloride is added to water and the mixture is stirred. So that is dissolving. So it's dissociation of a crystal. So more disorder, right? And why? Because calcium chloride dissociates into aqueous ions and more particles are produced. So dissociates and more particles are produced. I'll just take the reasoning for that. I mean, they just gave a general reasoning, which is that solid being converted into an aqueous solution. So we kind of gave a more in-depth reasoning. So they more, I mean, this one is a better reasoning. The change corresponding to the lattice energy of calcium chloride takes place. You haven't studied lattice energy yet, but this is what lattice energy is, or the equation for lattice energy. So what is this? Less disorder or more disorder?
Less.
Okay, why? Because number of gas particles are decreasing. Gaseous ions are turning into a solid ionic lattice. So this is delta S. Delta S negative, right? I'll check. Gaseous ions being converted into a solid. So give the full name of the term delta G. That's Gibbs Free Energy, or I mean, that's it. Gibbs Free Energy. Sorry, Gibbs Free Energy change. They actually underlined that. Delta stands for change, so make sure you don't make that mistake. That's and you've got a not on top of it, so you have to write. I mean, although they ignored standard, but standard was also there. This is standard Gibbs Free Energy change. And similarly, a lot of people make this mistake. I make this mistake, which is that if somebody gives you, remember the delta always stands for change. So make sure you use the term change. This is enthalpy change of formation. So there's a change that's happening. So, and similarly, this is Gibbs Free Energy change, not just Gibbs Free Energy. I think in the notes I made the mistake as well. So make sure you correct this, that it's not just Gibbs. G is Gibbs Free Energy. Delta stands for Gibbs Free Energy change. Describe how the temperature at which the reaction becomes spontaneous can be calculated, including an equation. So it's, I mean, just delta G is equal to delta H minus T delta S. I don't know what the explanation is apart from this. You just plug in the values. Sorry, describe how the temperature at which the reaction becomes spontaneous. So they're asking for how would you use this? So you're going to state that delta G would be less than 0 for this is the explanation that they were looking for the reaction to become, I mean, that's the second mark for. ठीक है, is this clear? This one.
Yeah.
And I'll probably skip this one or not. I mean, I won't skip this one. I mean, I'll just, he says, suggest an explanation for the difference, although you don't know what this is exactly because you haven't studied this, but let's think of it as an equation, just a simple equation, a normal equation. So this is disorder increasing. So why is there a disorder increasing? Because you had 3 particles, one of this, so you had 2 particles, right? And in the product side, you had 3 particles. So one of this and 2 of these, so that's 3. So you can say that the number of particles are increasing. So there's disorder increasing. And over here, the number of particles, they remain constant. You got 1 of this, 2 of these, 1 of this, and 2 of these. So the number of particles on both sides are exactly 3. So over there, there's a disorder increasing. And over here, there's not much of a change in disorder. So which is why delta S is more positive in this one. So that's about it. Although you can kind of ignore this question for now. Let's any other ones. I mean, let's just go through some. I mean, most of the questions are very typical. Calculate delta S, and then use the value to calculate the temperature at which this reaction becomes feasible. So pretty much the same one. Do you predict the sign of entropy change for this reaction? So lead 2 oxide can be made by heating lead metal in air. So solid, this is gas. So it's pretty obvious that the entropy change for this reaction is negative because the gas turns into a solid. So any difficult ones? Why is this negative entropy change? Because entropy is decreasing, gas turning into a liquid, or the number of gas moles are decreasing. Now in this question, they're asking, I mean, this one, it's the same formula, except that they're asking it the other way around. They're asking it the other way around because they've already calculated delta S. So delta S is already there. That's minus 2 to 5.7. The product SiCl4, that's also there. That's 239 and minus the reactant. So silicon is given, that's 18.7. What is not given is X over here. Cl2 is not given. So one of the reactant is not given. So the question is exactly the same, but it's just asked the other way around. That they gave you the answer, but one of the entropy values was missing, and they're asking you to calculate that particular entropy value. That's not given for Cl2. Okay, is this clear, this one?
Yes, sir.
And we can so he's asking calculate the temperature above which reaction 1 is not spontaneous. So that means delta G must be greater than 0. That means delta H minus T delta S must be greater than 0. And you just plug in the values. They've given you the enthalpy value, that's minus 640. And you already have the delta S value. I mean, all these values are given, that's minus 640. Delta S was also given to you, which is over here, that's minus 225.7. Okay, that's also given. Make sure all of them are in kilojoules. So I'm going to divide that by 1,000 and I'm just going to solve this. And again, be careful with the inequality. Like if you get rid of the negative sign, the inequality switches. So this would be minus 640 and greater than T minus 225.7 over 1,000. You get rid of the negative sign, the inequality changes direction. And this thing will go to the other side. So it will be into 1,000 and divide by 225.7. Okay, so all of the stuff was already provided to you. And anyways, you can ignore question 10 for now. It's slightly related to organic chemistry. So yeah, I mean, you can try doing this, but the answer might be given somewhere, but ignore this because you have to understand polymerization, all of that. So you can sort of ignore this one for now. So all the questions, very typical. It's the same thing over and over again. So we'll try and do lattice energy tomorrow then. Born-Haber cycle and lattice energy, that's completely separate than entropy change. Okay? Make sure you submit the worksheet on the Google Classroom, right? So does anyone have any questions for this? And also remember, the only confusing thing in this whole chapter is where they don't give you the values and you have to figure out what happens when you increase temperature, decrease temperature to the feasibility of a reaction. Does delta G become more negative? Does delta G become more positive? I mean, this part. Okay, that is the only thing that, where's the part where I made the table? I mean, it's this part. Okay, that's the only thing that people tend to get wrong or make silly mistakes. I mean, you do understand this, but it slightly gets confusing to just figure out without actually entering values, to figure out what will happen if you increase temperature or decrease temperature to the value of delta G. That's the only part that kind of makes this slightly tricky. Okay? So let's continue tomorrow then. So ये कोई question नहीं किसी का? चलिए ठीक है, okay everyone.
Laughing.
Take care, Allah Hafiz.